War Thunder claims to be one of the most realistic combat flight games ever made. But how close are its aircraft flight models to real physics of warbirds and modern jets? Alright, so before we judge the game, we need to understand what a flight model is. In aerospace engineering, a flight model is a mathematical simulation that predicts how an aircraft behaves in air. It calculates things like lift, drag, thrust, weight, control surfaces response, stall characteristics, energy retentions. These forces determine how an aircraft climbs, turns, stalls, accelerates, or decelerates. In War Thunder, developer of Gaijin Entertainment uses two main types of flight models. First is the standard flight model, which is very simplified for the beginner gameplay. The advanced model calculates aerodynamic forces using air, wing surfaces areas, aircraft weight distribution, control surfaces, deflections, engine thrust curves. This means each aircraft behaves differently based on its real design. In the aircraft forces, we have three axes of the aircraft motion. Before understanding the control surfaces, we need to understand the three axes of the motion. The aircraft rotates around three axes. Number one is the roll, rotation along the longitudinal axis. Number two is the pitch, rotation along the lateral axis. Number three is yaw, rotation along the vertical axis. Each axis is controlled by a specific surface of the aircraft. Number one, the rudder. The rudder controlling the yaw. The rudder is located on the vertical stabilizer of the tail. It controls yaw, which is the left or right movement of the aircraft's nose. Pilots control the rudder using foot pedals. When the pilot presses the left pedal, the rudder deflects left. Airflow pushes the tail right. The nose turns left. The rudder is especially important for coordinated turns, crosswind landings, correcting adverse yaw. Number two is the elevator. Elevator controlling the pitch. The elevator is located on the horizontal stabilizer at the tail. Its job is to control the pitch, meaning whether the aircraft nose moves up or down. When the pilot pulls the control stick back, the elevator moves upward. This deflects airflow downward, generating a force that pushes the tail down. When the tail moves down, the nose rises, causing the aircraft to climb. Push the stick forward, and the opposite happens. The aircraft descends. Number three is the aileron controlling the roll. Ailerons are located on the outer trailing edge of the wing. There are two of them, which left aileron and the right aileron. They move in each direction. Let's give you an example. When the pilot moves the control stick to the right, the ailerons goes up. The left aileron goes down. This creates differences in lift between the wings. The wing with the lowered lift drops, causing the aircraft to roll toward the side. This is how an aircraft banks during turns. Well, why all three work together? In real life, pilots rarely use just one control surfaces. Turning an aircraft properly requires coordinated use of all three controls. The ailerons to roll the aircraft into the turn, elevator to maintain lift during the bank, rudder to keep the turn coordinated. This combination ensures that the aircraft turns smoothly and efficiently. Even though the aircraft designs vary, the basic control system remains the same across almost all the aircrafts. To summarize this, ailerons control roll, elevator controls pitch, rudder controls yaw. Together, these three control surfaces allow pilots to fully control the aircraft in three-dimensional space.